Howdy, today on Flipping Science, we're looking at amides. So science understands we're going to look at carboxylic acids undergo condensation reactions with amines to form amides. So draw the structural formula of the amide formed from a carboxylic acid and an amine. Draw the structural formula of a polyamide, given the structural formula of monomers. Condensation reactions, again we've got this one. So making amides is a condensation reaction, so we've got this understanding again. And amides may be hydrolyzed under acidic or basic conditions. Identify the products of acidic or alkaline hydrolysis of an amide. So amides are produced from the condensation reaction between a carboxylic acid and an amine. So you get this group being produced. So this is the amide group. So C double bond O N. Depending on which carboxylic acid and which amine you've used, you could have just a hydrogen on the side here, and then we could have a carbon chain on this side. We can have a long carbon chain on this side. It really depends on which carboxylic acid and which amine have reacted together. But the C double bond O N, that's what you're looking for in an amide group. So here's a general formula for the production of an amide. So we have our carboxylic acid with our R1 carbon chain. That's reacting with an amine with an R2 carbon chain. And you react those together and you get your amide. So here's the C double bond O N. You have your R1 carbon chain connected to the carboxylic acid because that comes from the carboxylic acid. And you have your R2 carbon chain connected to your nitrogen because that came from the amine. When that happens, you get water coming out, and that's why this is why it's a condensation reaction, because water is produced when the amine and the carboxylic acid react with each other. So here's an example. We have acetic acid, systematic name is ethanoic acid, reacting with methylamine to produce N-methylethanamide and water. Now, it's important that you know you don't need to be able to name the amides that are being produced by these reactions. You just need to be able to draw with the product. So we have our two carbons from the acetic acid, so this is our two carbons here. We've got our double bond O, so the carbonyl group from the carboxylic acid. And then we've got the one carbon that's attached to the amine in methylamine. That's over here. So we get C double bond O NH. And it's important to remember that C is bonding with that N, not with this H here. And again, we get water being produced because it's a condensation reaction. So let's talk about polyamides now. So nylon is a very common polyamide. It's used in clothing a lot. The bristles on your toothbrush are nylon. It's used in stockings. So it's used all over the place because it's very stretchy, and it's very strong, it's very resilient, and it's got properties that we like in our clothing, so that's why we use it there. So how do you make a polyamide like nylon? So you need to have lots of amide groups being produced. So to do that, one manner is by reacting a diamine with a dicarboxylic acid. So a diamine has an amine group on either end of the carbon chain, and a dicarboxylic acid has a carboxylic acid on either end of the carbon chain. So you react those together with, in this case, using acid and heat, and you get your amide group being produced. And water comes out, because again, it's a condensation reaction. This reaction can continue. You can react your amide that's being produced. If it still has its carboxylic acid end and an amino end, they can react with other amines and carboxylic acids and continue and continue and continue. And that's how you get the long chain polymers forming. So over here we've got nylon, so a specific example. So this is nylon 1,6. So here we're using diaminohexane, so this is our diamine because it's got an amine amino group at either end of the carbon chain. Then we've got adipic acid, which is our dicarboxylic acid. You react those together, a water molecule comes out, and you get your amide group forming, which is the C double bond O NH, C double bond O NH. And those units repeat themselves over and over and over again, and that's how you get your polymer, your plastic being produced. So you can also produce polyamides from reactions with amino carboxylic acids. So what's an amino carboxylic acid? It's simply a substance that has an amino group at one end and a carboxylic acid at the other of the carbon chain. So if we have a look down here, we've got our substance down here with our R side chain, our variable side chain. It's got an amino group down here, and it's got a carboxylic acid group over here. You react two of those together, and you get your amide group forming in the middle. So that's the C double bond O NH down here. So that's, and you can, again, keep on doing that over and over again, and you get lots of those joined together, and you make your polyamide. And again, it's important to remember, every time this happens, you get a water molecule being produced. Now, amino acids are very important in your body. We're going to talk about amino acids and proteins later. They're examples of amino carboxylic acids, so let's have a look at them briefly. So these are the amino acids that your body uses to make all its proteins. You can see for every single one of them, at one end it's got an amino group and the other end it's got a carboxylic acid group. These are drawn in what's called the zwitterine form, which we'll talk about later. The hydrogen from the carboxylic acid group has gone over to the amino group and protonated it. But these 20 amino acids, they're what are used to make every single protein in your body. So we'll look at those later on. So now we need to look at hydrolysis. So hydrolysis is when you use water to break up a compound. In this case, we're hydrolyzing our amides. So under acidic conditions, so here we're using hydrochloric acid. If we have a look at ethanamide here, the product we get is acetic acid and we get an ammonium salt. In this case, it's ammonium chloride. So under acidic conditions, you get the acid being returned and you get an ammonium salt. So let's look at another example. So here we have this amide over here, so we've got a C double bond O-N. In this case, we've got two methyls attached to the nitrogen. So adding in our acid, in this case I'm not saying which specific acid it is, I'm just saying we've got hydronium ions going in. So under acidic conditions we return the carboxylic acid that we would have started with, so C double bond O, so H, C double bond O, OH. So in this case it's methanoic acid. And then you get your ammonium salt. So in this case we've got our nitrogen is attached to two methyl groups. We get another hydrogen attaching to that, and another hydrogen attaching to that. So then we have 4 bonds on our nitrogen. The extra hydrogen there gives it a positive charge, and it's very important you represent that positive next to the nitrogen. That's very important. And that's the ammonium, the positive parts of the salt that we would get. So again, it's very important for this. Under acidic conditions, you return the acid from the carboxylic acid part of your amide. Now, you can also do hydrolysis under basic conditions. So in this case, again, we'll look at ethanamide. We're going to do it under basic conditions this time. Now, under basic conditions, rather than getting the acid being produced, you get a carboxylate salt being produced. So a carboxylate ion with the positive part of the base present as well. So in this case, the part that would make an acid under acidic conditions, if you react an organic acid with a base, you get a carboxylate ion being produced if you do that. So in this case, we would have had ethanoic acid being returned, but if you put ethanoic acid in sodium hydroxide, you'll get a reaction happening, and you'll get a salt being produced, which is sodium ethanoate, and that's all we're doing here. So under basic conditions, rather than getting the acid, you get a carboxylate salt being produced. The other part you get is your amine being returned, the amine that would have produced the amide to start with. So in this case, we've got NH2, you gain an extra hydrogen to make NH3, you make ammonia. So this is a very simple example. Let's look at a bit more complicated one. So again, we have our same amide from before. We're acting it with sodium hydroxide. So under a basic condition, we get our carboxyl anion being produced. So that's the CH3COO minus that we're getting here. Because we're told the specific base, sodium hydroxide, the sodium ions we can represent next to that. So that's the positive part of the base. So we get sodium ethanoate. So this is our salt that's being produced. Now, the other part we get, we need to add an H to the amino part that would have been here. So we get C double bond O-N. So now we need to put an H on here. That comes from the hydrogen here. So that goes there, and we get our amine that would have been reacting with our carboxylic acid to make our amide to start with. So under alkaline hydrolysis, it's very important to remember that you return the amine, and the other product you get is carboxylate salt. So under acidic conditions, you get an acid. Under alkaline basic conditions, you get the amine. So today on Flipping Science, we looked at amides. That's it for Flipping Science today. See ya.